Morning. Morning, Howard.
Good morning. I gotta bring my microphone down here. You and me again, early. Well, not early, really that early.
We're right on time.
Yeah,
Yeah, I forgot.
I just hung up from a lubricant immersion cooling call.
Oh, nice.
It is really pretty interesting change in uh, method of cooling, 6 fans on the back and things getting hot and distribution of heat but at the same time immersion immersing immersing absolutely everything in a giant bucket is scary, considering if you've got wires that the liquid's going to wick up the insulation, or it's going to
Right.
damage the components or flooding the space and the time I've spent in dealing with high-speed cables and wiring, we now have flyovers, that plug from the back because the board isn't fast enough to transmit to the big chip in the middle. Struggling with fluxes wicking up the twin X and trying to wash things out and things getting worse, and to think that we're going to fill up this whole bucket with liquid is kind of scary from a signal integrity standpoint, if nothing else.
Well, yeah. No, I can imagine from the connector side of things, it does play havoc.
Yeah, I mean, the amount of time and effort that goes into high-speed backplane connectors or high-speed cable connectors, where you have this huge bundle of cable, the subtle changes that you change to widths and thicknesses and spacing and grounding. And now I'm going to take all that Teflon cord stuff, that the cables, where the Teflon cores are mostly air, and then we're going to immerse them. So, yeah.
Interesting. The
And
Teflon cores are mostly air, are they?
if you think of a twin X, okay, a blue wrap twin X with a shield around the outside, just asking for a capillary action, right?
Okay. Interesting.
That foam insulation that circles the high-speed lines, the objective is to make the dielectric constant as close as possible to 1, so that, and that stability, if you take and dig your nail into that cable or bend it too tight, you squeeze that air out of that foamed Teflon. Well, now we have PFAS problems because it's Teflon. It's the objective is to make it air, so that you can have a dielectric constant from very accurate spacing wire to wire, and the foil wrap that goes around. Like I said, capillary action is just what's going to happen when you dip this thing into liquid. So, yeah.
Interesting. So we might
Yeah.
be on to something here by separating the wet side from the dry side with our efforts.
Yeah, but now it's not like we have lines buried in a PC board anymore. Certainly
No,
we do,
well, that's
but
done and dusted. We don't need motherboards anymore. They're a waste of time.
not the backside, no, but inside the little one, the pizza box server,
Oh no, right. Yeah.
we have the cable comes in through a connector that you can take apart and put together, which means that's 2 spaces full of little tiny pockets, right, that plug together. And now, instead of drilling down into the board, wiggling around through the inside, we have onboard cables So it comes in on a cable, joins to a cable, and it flies over in like a giant spider of high-speed data cables. How do we immerse this thing without having serious signal integrity, as well as, the plastics absorbing the material, all the solid state drive stuff that, no. Anyway, interesting.
So,
Oh,
so Matt, is Samtech solve this, Matt? Good morning, Matt and Mitch.
Yeah, we just solved it instantaneously.
well, that's
There
what
you go.
Samtech's all about.
No, I mean it's Howard's raising some interesting concepts the industry's tackling right now. So
Yeah.
it's gonna be interesting to see how it plays as time goes forward. I this is just my own opinion, but I think what's gonna force this is the disruption that's coming in AI. The the next gen AI chipsets coming out with 1K watt, 1.5K watt,
Oh my gosh, incredible amount of current.
2K watt.
Yeah.
To me that's where the data center industry has been messing around with this for a while.
Right.
But I think the AI with the new AI chipsets and the insatiable demand for AI, I think it's going to force it more than the data center folks will. So it's going to be interesting to see how it all plays out over the next year or two. And someone's going to have to come up with a solution and solve a lot of these problems. So it's interesting. I'll just say it that way. It's interesting.
So
how it's going to play out.
Be prepared for a new connector that goes onto your laptop that attaches to a chiller under your desk.
So
Well, sort of the
go on.
yeah. Well, the boundary from my perspective is the Zebra system. So I worked there for 9 months or so, and it's I still abide by their confidentiality, but it's effectively a something north of 15,000 watt thermal envelope for a thing the size of a dinner platter.
Yeah.
So
You could
they're pushing well north to 15,000 watts into this, and then pulling off thousands of. Yeah.
I think my furnace in my basement here is 15,000 watts. Think about those as 100 watt light bulbs. There's a lot of heat.
Yeah.
You need
it. Forget what.
Sorry, Mitch. Go on.
I forget what residential wiring. I used to know it off the top of my head. It's the residential wiring for a standard home is only in the 20.
Yeah, it's
14
100 amps, right? So it is a small home or you have 200 amps for a bigger one.
Right. In the wall, we have a 14 gauge, which is good for 15 amps. And in the kitchen, we have 12 gauge, which is good for 20 amps. And we're talking of multiple orders of magnitude greater than that. And you can plug in a handful of toasters in your kitchen without breaking the circuit breaker. But 1,000 watt toaster.
So, just to wind this back even to the simplicity, I was about a year ago now, I was at my friend's house, and he's got a teenager that was earning some pocket money and decided to buy himself a $2,000 gaming machine. And he had an 800 watt power supply in there, and his room would be baking. They'd have to turn the entire house air conditioning on, even though it's in the winter, to cool his room down. And so, this is where it strikes me is as we go forward, if we're looking at this energy reuse, you would architect your homes just like you do for watering our power in the walls. You would architect for the actual compute to actually be integrated into that thermal management system, a bit like Tesla evolved on their cars.
Yeah. So if he's running that on a regular, what we would have here, 110 volt line, he would need more than a 20 gauge or a 12 gauge 20 amp line. It's just If it's in Europe and you have 250 volts, you can get by with some thinner wires, but not here where we're running at 110. It's just you
So, well,
trip the breakers.
Yeah. So, I mean, just on that note, it's an interesting conversation, and I guess what we're all getting to here is, you know, when we look at it from your on the interconnect side of things, we see a bunch of issues coming up. I mean, we've shifted to cables. Motherboards seem to be no good anymore over 100 gig, you know, then we've got the thermal management side, we've got the power delivery side. So we've got all of these issues going on, yet we still try to continue. So what we're trying to do here, I mean, is people start to get closer to these challenges that I guess I see ahead of time. That they begin to realize that we do need to start again. Now, and NVIDIA are doing lots of fascinating things. It'll be interesting to see how they deal with the cooling solution. But I was talking to go on.
Yeah, Alan, I think the opportunity for your project is to really concentrate on this 1,000-watt envelope that's coming up.
Yeah.
And because it's pretty much kind of leaked out that NVIDIA is going to have a 1,000-watt GPU.
Yep.
And
they said they're going to have a liquid cooling solution for it as well, right?
Right. So there's a lot of dancing going around about how it's going to be cooled and so on. But however, the real unknown at this point is that today they put these together in groups of 8 in their NVLink with the SXM module.
Right.
And now if you do that, now you have an 8,000-watt pluggable unit tray that no one individual can pick up.
Right.
It weighs too much. So the real and the CHEM form factor, the PCI Express CHEM form factor is completely out of steam. Right. That pluggable form factor is I mean, they're going to push it to 650 and these intermediate wattages, but it's a complete retro kludge for powering and cooling it.
Right.
And so now the opportunity is in the OCP community, what's the 1,000-watt pluggable form factor, and how many lanes do we get off of it?
Yeah.
And then how do we cool it? And we know we can cool a 1,000-watt envelope with air. Everything's air cooled at the end of the day anyway, but it's a matter of how much space do you need to cool it?
Well, I think that's where the question goes as well. Is in the moment, it's like, where do they convert it to air? Is it in the back door of the rack? You know, is it some chiller facility separate? Is it so that there's places, right?
I think last week you had someone on that was, and I'll give up the floor here, but someone mentioned one of the large supercomputers that they at one of the national labs that they didn't properly, they didn't properly filter the water, and it caused them tremendous.
Yeah, that was Trent DeHooge from Lawrence
Livermore.
I think he's from.
Yeah, I hate to. Okay, so that was one national lab talking about another national lab. So I don't want to get in the middle of that discussion. I used to work for the company that built the one at Oak Ridge. But at any rate, if I go then revert back to Cerberus a little bit, it's fairly open, and you can go look at their system. It's water cooled, but it's a closed loop. It's a closed cooling system.
Well, so
and then they have a large heat exchanger at the rear that then converts, that you run the facility water through.
Right.
So you're not really pushing facility water through that incredibly complex heat exchanger that's pulling 20,000 watts out of the wafer.
Right. So I actually was on a call yesterday with Trent, and he brought a guy in that's had a direct experience with Frontier, and so they explained the issues that they went through. And
I would have liked to have been on that one. Was that an open call or?
It was an open call. Yeah, it was just it was sort of just anecdotal as opposed to but he was talking about the problem that they've got now is these fins, because you need to get as much copper surface area with the water. That these fins, they easily get blocked up. They're almost like a filter in their own right.
Oh yeah,
And
yeah,
this bacterial growth they get, and they have some super
Mhm.
bacteria that are trying to still find out what it is. It might have been
Um,
bred a new one, might have evolved.
yeah. Oh my God!
Whereas
Don't let it get out of the lab.
yeah, whereas idle, where the water is a little bit stagnant, even sort of where turbulence is, it grows, and then pieces break off, and then they block up the heat sinks of because of the fine mesh of the water flowing through the heat sinks. Anyway, it was a really good conversation, and again, it's a bit like this one that Howard was talking about with the interconnect. It's a case of, so I said, what are the solutions? Everybody wants to use water, and they've tried to use water because it's more conductive of the thermal. But they've got all these growth challenges, and it looks like they've all gone about it half-assed. And what they're all doing is they're all winding back to dielectrics, or 25% is PGW or whatever it's called,
Yeah.
which is another nasty stuff. And I said, well, hang on a minute. If we're taking it up to 65C, he said, oh well, yeah, the bacteria wouldn't grow. But then bacteria, you can get some sort of bacteria that will grow even in 85 degrees C. But so I was saying, if we're designing it from scratch, could we not maybe get some more expertise around this to actually think about all the challenges and see if we can come up with a full solution? And
well, they are, and for example, I'm pretty certain that I know it's secret, but I'm pretty certain that Zebra's patented what's running through their veins. They went to a chemist and worked on it. Now, and generally, nobody wants to go hot. Generally things are going cold.
Yeah, I know.
If we're going to go in a direction, it's far better to go cold.
Well, maybe not. And I think that's where the debate can be had, right?
Yeah.
Anyway, I didn't want to necessarily pollute the interconnect call, but I think
this all applies to the interconnect as well.
Yeah. Oh, absolutely.
But because
interconnect.
if we go to immersion, in order to pull the heat out, whether it's water, which everybody's in the immersion committee world is voting against, it's more of a mineral oil sort of fluid, but there are chemical antioxidants have to be dealt with that are mixed in, and then there's viscosity issues as this fluid bakes. How hot does it get? Is it a surface temperature issue that in the total amount of fluid that's passing through there, it's much cooler, but there are many places with hot spots. And so they're, trying to make a decision whether do we test this at 40C or do we test it at 140C?
Right.
And Howard, I used to be an old signal integrity guy, and so we always reused a different air dielectric for the outer two traces. Those trace widths had to be different. And you just brought up, I hadn't thought about it, but of course, if I was doing that, I would immediately think about it. You're going to put this oil on top of a completely different dielectric. Those outer two traces, top and bottom, are all going to run different.
Yeah. And if we're running twin-ax, and here are my friend Matt here from Samtec has to deal with the same thing. We have this great capillary piece, which is giant bundles of wires where we have connectors that are 12 by 12. There's a lot of capillary action that can occur, whether it's water cooling or whether and normally water cooling is done locally, not immersion, where absolutely everything gets covered with this low viscosity fluid. If the lower the viscosity, the better it's going to pull that heat out, but at the same time, the worse it gets. And you want your server, which is now in a giant puddle, to continue to operate at the NVIDIA rates that we had looked at before. And if there's 8,000 watt GPUs, yeah, that's 8 toasters running at the same time. That's a lot of heat.
And the
So-
irony there, just thinking even forward from an interconnect perspective, then we've got these two worlds. We've got these worlds where these processors are knocking a kilowatt and they're tiny relative in terms of their thermal density is huge. Yet at the opposite end of the scale, we've got QSFP going to OSFP because we can't cool 20 watts in a huge connector. You know, it's like nobody's thinking about, well, everything else is going to be getting hotter and it's getting bigger and everything else is actually bigger than the compute now. So, you know, what we need to do is we need to take a step back and look at everything, right? And that's what we're trying to do here. So, which everybody, I guess, we all understand. So in what we're doing here, obviously, I guess we're all up to speed on the module itself, that our connectors are dry side. And we do have a wet side, and it can be different implementations on the wet side, which we've been talking about in terms of a traditional water copper type lid, where it is still dry, or a little mini immersion chamber, which we're investigating. And I did talk to those guys, you know, about the Frontier in Trent, just about the, in theory, if the University of Illinois research of this conformal coating, they claim that that's about 7 times more efficient at transferring the heat, the lower resistance for the heat from the die to the copper surface. And then if we do boil it, that's another 7 times. I don't know where the magic 7 comes from. But so that's 49 times more efficient than and then I think water is at least twice as good as the best dielectric in terms of conductivity. So that's like we're knocking on the door of 100 times more efficient. And as the guy said, he was saying that you're blocking the filters. You know, if you could make the channels bigger, not so small, maybe you could get over the blocking and get the filtration somewhere else. And this is where I think there's an opportunity for design to come in to know about these issues and to try and work together and solve them. So hence I bring us back to this universal interconnect. I guess we left the last meeting, I don't know if you were all on, but we left the last meeting with obviously the DOE. By the way, I'm getting more and more bullish that if we can actually put a decent proposal together, which I think is a big if, that I think we can get some serious funding here. I really do. It's a shame that we can't get any of the big boys to actually want to do anything in the open. They all seem to be more than happy. I mean, if we look at talking about what you guys have been talking about, we're going to see what NVIDIA does with their kilowatt, right? But if we look at the Frontier machine, the Frontier machine is 2 nodes in a 1U server. I think it's 1U, with the OAM module, with a water cooling rat's nest going on. You know, so that's the MI250Xs, which I guess were in the probably 500 or 600 watt range. But that was a 1U box. It must have been sitting around, well, 1, 2, 3, 4, you know, at least in the order of 8 to 10 kilowatts already, right? If I got that right, 1, 2, maybe 5 to 6 kilowatts for that 1U box. And then it had a slingshot switch in it as well. So, you know, it's a mess of a design. Well, it's not a mess. It was beautifully elegant when you looked at it. But in terms of serviceability, you've got to service it by the node, right? So when one module goes down, you've got to take no IT guy is going to come and service that, or you know, you're going to have to come and completely replace the entire double node box. Anyway, so it feels like we are beginning to realize the ramifications on all angles. And from the connector perspective, from your guys' perspective, if we can keep these cables and connectors dry, like we can with our approach, and we can conductively cool active cables in a much smaller form factor, because we can have conductively cooled to the water channel on the manifold. Then we can shrink instead of going bigger onto OSFP, we can come down to the size of these cables that are inside a server today. Then we've got lots of opportunity here. And when we think about ourselves in isolation, it's easy for us to go, well, that's not the way the industry's going. The industry needs us to solve immersion, cables in immersion. It's like, well, they don't if we think about the entire system design. But then they said, then obviously each company says, well, that's not our bailiwick. We just focus on, so therefore the silos remain, and we never work across the silos. And that's the hardest thing about what we're doing here, is we're working across these silos. And DARPA doesn't see that as DARPA hard. If it's not brand new material science, it's not DARPA hard. But I think maybe the labs are beginning to see this. It'd be interesting to see how NVIDIA solves it. If NVIDIA have been listening to these calls, then you never know, they might be copying some of it and making it proprietary as they do. Anyway, so in terms,
I think we'll hear from them in a week or so at GTC.
Yes, of course. Yes, good point, Mitch.
At least some information on a roll out of that.
Yeah. Oh yeah, I'm sure. Yeah, no, good point. Well, it'll be interesting to see how they've done it, whether they do a frontier type approach or they completely reinvent the box for the water.
Well, some big data center is going to do it, and it'll either be a large government contract, but those take years to get done. So it most likely it'll be kind of buried inside one of the big cloud service guys.
Yeah. Well, they're going vertical, right? So they're even building their own data centers. They might be building they might have designed a data center from the ground up for water, like we're trying to do. But they're actually doing it because they got the money. But again, that's the trouble. If you look at OAM versus what NVIDIA have done, here in OCP, we're great at saying, oh, look what NVIDIA have done, let's copy that. But we end up being 5 years behind all the time. And so we need to sort of think for ourselves, for the industry. We've got a lot of talent in those small companies, and then drive it forward from the front foot rather than the back foot. And really AMD and Intel, because they don't have access, because NVIDIA is way ahead of them. It seems anyway. Well, we'll see.
Well, Intel are the leaders on pushing forward this immersion cooling. They know they need it. And,
yeah. But again, they're doing it from an evolutionary. So you've got this swimming pool that you dip your traditional servers in and give you guys all the issues, right? So again, even Intel don't have a clue what they're doing as far as I'm concerned. This liquid cooling is right, but you got to think about that. How can you do this better? I don't know. That's my view.
Well, a lot of activity going on now with liquid cooling of assorted methods.
Yes. I'm no doubt. The other argument is, well, we get rid of electrical connectors, just go to optical straight away, right? So,
well, you still have to. You have VCSELs, and you have a lot of energy goes into those as well. So you have the same issue. And do you really want a puddle of liquid at your optical interface?
Well, that's true, I suppose.
Yeah.
So it's a lot of problems to resolve. I guess what's his name? Andy Bechtolstein whatever the switch company is. He was sort of saying, you know, co-packaged optics is fraught with, you know, challenges of scaling up. So
Arista, isn't he? Arista.
Arista, yeah,
Networks.
yeah, Arista, yeah.
Well,
Anyway,
then there's the other optical company that takes the light source out of the package or off the die. I forget their name. Starts with an A also.
AR Labs.
Yeah, AR Labs. Yeah.
Right. So anyway, so I guess back to our, I think where we came to with regards to what we're doing here in this group is, can we build this universal interconnect? So as we've been talking the thermal piece, we've got this thermal integration of a conductive path from any active circuitry in a cable to a cold plate to shrink an OSFP down to one of these MCIO size connectors. So you've got that piece, which would be quite a nice innovation for the industry. And because we're seeing, by the way, I mean, to restate, we are obviously seeing the likes of Lightelligence were showing off their little photonic optics engines, although they had 32 fibers coming out of it, so I don't think it's practical. But the actual photonics and electronics around that was a tiny little chip swimming around in these big QSFP cages, and they're already shrinking it down into MCIO type sizes, but MCIO doesn't have any power on it, despite its previous generation Oculink having power on it, because they were hoping for optics in the previous generation and not in the current. So they're making that connector even bigger to accommodate some different power configurations. That's like powering the module at the other end, rather than just powering the cable itself. So you know, so we've got an opportunity here to make this universal interconnect. I guess the paddle card thing we've gotten over to say, well, okay, we can make that work as it is in the MCIO. We can, I guess, even if we can't go up to the 224 on a passive cable, we could probably quite easily do 224 with an active cable, with components, with retimer components in the connector itself, in the cable itself. Obviously, or silicon photonics in the cable itself for near packaged optics, and then the potential for co-packaged optics that we've discussed on this call many times now. So I think what we really want to get going is we really want to get going with what we want to get what do we put in the proposal to say this is what we're doing. And I guess my only other thought process was OCP like specs. Could we actually start writing a spec, a base spec for this universal interconnect? And so we could maybe put some basics in there of what this is going to look like. And then that can go forward as part of our proposal is this is what we've done so far on the specification. We now need to make this interconnect in a few cable examples, and that's part of the funded POC that hopefully the DOE New Frontiers would fund this universal interconnect. So that would be so can we make progress there, or if we can't make progress on getting the spec together, what can we put in the proposal that gets enough clarity and shows why this is a good idea? I mean, I think, Howard, your arguments on the challenges with immersion cables and serviceability, et cetera, you know, these are all good pieces to say this approach keeps us in this dry side world. You've got a dry side of the module and a wet side of the module, and also having the local conductive cooling is helping us to do these miniature active cables. And I think that the idea that we're packing 1,000 watts into a GPU, yet nobody's paying any attention of going between 1 watt and 10 watts in an active cable or whatever it happens to be. And how do we miniaturize that, or do we all leave all that stuff still huge? You know, we want to be shrinking everything else along with the shrinking electronics in the package. So anyway, how do we get going on this document? I guess is a question. Now, Matt, I guess you guys on the last call we were suggesting, or I was suggesting, that the direct cable to connector might be a good idea, and if Samtec were prepared to open theirs. We've got the MCIO one. I guess there's challenges for you at that end, so we've moved. So it looks like we're landing on the MCIO. So I think the plan of record right now is our starting point is the MCIO connector as it stands today. We just redefine the pinout. Maybe we put a slightly different keying on it. We begin to do some 3D models of how would we. Maybe we could, throw together a little active cable if we've got some active examples. Maybe we could turn to. We've got Avicenna that are sort of coming and going. I'm not sure. Mel from Avicenna pops into some of our calls, but I'm not seeing a strong engagement from them. They're certainly interested. But also maybe we could get Light Intelligence or one of the other optical companies to actually maybe throw in a model. So I mean, if we could, even if we could start with a little model of this connector that actually, obviously Amphenol Z from Amphenol did help out quite a bit. If I share. So if I share my screen here. So back a while ago now, Z did actually modify the MCIO 3D models to show a couple of potential examples of the surface mount, of a completely surface mount version of the TA1002 and of the MCIO. So he showed surface mount versions of that, and then he made up a quick thermal gasket example, although this doesn't really work because we need this to be a copper chunk that actually lands on top of, or some sort of a assembly between this and a copper chunk that lands on top of the active components. How does this affect the body design of this as well? And how does it mate with, if I bring the 3D model in, how does it mate with this? So when we mate, we want to be able to make a contact with this. And I think we probably need to tweak this manifold design to actually put a container around here so that when the cable pushes against this, it doesn't bend the connector, it pushes against the body on the other side. So so maybe we want to extend the shell a little bit further around. So yeah, so I guess one thing we can do is we could just advance the model if we have some modeling resources of what would this look like, and maybe from that model we can start to shell up a spec. So as the connector guys in the room, sorry to put on the spot, Matt and Howard, I mean, do you think that you could possibly get some resources to, I guess, Matt, you guys don't have an MCIO, do you? So you don't have anywhere to start from.
We don't, and I think that would handcuff our support from that perspective. But the general approach that you're taking, I think, makes a ton of sense. I
mean, obviously, we've got the public models that the likes of Amphenol have obviously released. Obviously, it's a lot easier for them. They got the detailed models rather than the simplified public ones. So,
well, hasn't MCIO progressed? Isn't it something? I think they got some new names for it, and it's progressed some, hasn't it?
So MCIO, as it stands, can go. I think they go a path to PCI Gen 6 with it, and then they've extended it. They've made it longer, which in order to accommodate the power. So, and I don't really want to make ours any bigger, and we only need 66 pins as opposed to this has already got 74, so we can allocate some of these pins to power. We just need to rekey it. So the feeling I've got here is there's a number of manufacturers that already make this in quantity, right? So this seems as good as anything for us to bolt onto if we think it's got the mileage to get us. I don't think we want, well, never say never, but 224 gigs seems to be, I don't know. Do you see us going to 400 gig, Matt, or Howard, from where we are at 224?
In 2030.
In 2030. Okay, so we got a few years there.
That's just no. I say that jokingly, Alan. There's a ton of challenges to 224.
Yeah, right.
In the mid, in the near to midterm. So 400 per channel is 5 to 7 years out.
It looks like we are getting to this crossover point of optics now, right? I mean, that's I don't know, but we've said that for many years. I guess you can argue. We always find a way around it, but yeah. But my feeling is that, and I don't know. I think some of the optics is actually ends up being a lot cheaper. It's the energy required, right? I mean, the amount of power required to drive these. You know, when you look at picojoules per bit, but the trouble is we're trying to get terabytes per second out of these cables now. So that's a huge amount of energy when you keep multiplying up the bandwidth, unless you switch over to something that's far more efficient, which is a promise of silicon photonics, right? So, so yeah, I think as long as we can get up to 224, my mental picture is if we can do passive cables with this interconnect at you know, a decent couple of meter length sort of thing with 34 gauge cable, then that's good enough. And then maybe we need to go active for 224, but electrically we can bring 224 into the connector paddle card, and then we go active or optical. So I think we design around a 224, and if somebody can get the interconnect design so they can do 224 with passive over a couple of meters, then happy days. And they can make some maybe tweaks to their connector design without changing the footprint. That's a possibility as well. So I think sort of hanging our hat on the MCIO as it stands right now is not a bad starting point. And then modifying these is it's a keying effort to make sure that you know only our new universal one can plug into it. And then it's changing the design of, like, this body probably could do with changing, or the way it latches could do with changing, so that we make the conductive path to the cold plate nice and efficient and simple. So maybe the body of these connectors, but not the primary. This is just metal bending change. So am I right, guys, that it's relatively easy on the metal bending changes as opposed to the fundamental design of the interconnect?
Yeah, so you can, there, as we know, there are all kinds of cages and boxes and shielding and latches and everything that goes along with these.
So it's a relatively low cost tweak versus designing a connector from scratch.
Stamping dies and etc. Yeah.
Yeah. So, I mean, that's where I think we need it, obviously, because going back to the model again, you know, obviously for these connectors, the shells of the cables that plug in here, because you can either plug media in or a cable. So we'd need the shells to be slightly redesigned, and they could be active as well. And so it's a thermal piece of this, of suddenly we can, you know, and I think Avicenna actually is their first product is a QSFP cable with their tiny electronics in it. And they were quite excited by we could put that into this internal interconnect very easily. So, you know, assuming they're successful with their QSFP cables, it will be a fairly easy mechanical transfer for them into this format. So that would be an interesting for the active cables at least. So that would be an interesting demonstrator. The only other thing we've got as well, which I don't know how much you guys are motivated by, you stop share. I'm not sure on how much you guys are motivated by a real application. I know to get your management's interest, somebody with a big fat checkbook, you know, would buy a lot of these. Suddenly, everybody wakes up. But this FPGA emulation platform, which I was talking about on the main call last week, I think is a big opportunity that I think we could do. I think what's happened to the FPGA emulation platforms is there was lots of different smaller companies doing it. As I said, the Analytics business in the early days, it was about 25% of our revenue was accidentally, we never sold to these guys. It was in the ASIC emulation with FPGAs when we had 7 FPGAs on a PCI card. And I get the impression only Synopsys, Cadence, and Mentor, Siemens have these emulation platforms now, and it sounds like they get leased out, or, you know, it's like a cloud service where you go from simulation to emulation. And it sounds like it costs an absolute fortune, because I'm talking to a few companies, silicon startups, where they're saying, where can we buy an FPGA card and we can start to do our own emulation on an FPGA card? And how can we gang them together? So, and when you look at that, you've got regular PCI cards, or you've got, or you might have I don't even know if there's many OEM ones, if any OEM ones around.
So Alan, I haven't kept up with the two. What are their, without disclosing their actual thermal envelope, where are they headed for their largest FPGAs?
Well, so well, it's pretty public, because you can download their power spreadsheet, and you can pump in the flip flops that you think are going to toggle and all that, right, Mitch? You know,
right. They're always been kind of cagey about that, but
well, no.
So rough numbers,
so
where are they headed?
I can give you my numbers. So basically, as an Alitech, we just took the publicly available power spreadsheets that Xilinx would give you, and we would load up the design with, like, you know, certain toggle rates in 100% full, 80% full, and that was how we got the absolute maximum power. So I basically went through that exercise with their latest. Well, it might have been the VP 1802, not the 1902. But long story short, you're definitely in a sub 500 watt range. You're probably operational. You're probably in a 200 to 300. But okay.
You can't, you know, you can't shoot behind the duck. You got to know they're designing their next chip right now, you know, and it's going to be, and they're having to decide what that thermal envelope is going to be, even as cagey as they are. So it's either going to be, you know, so that's the thermal envelope. Let's say it's, I don't know. And I always had a problem with saying, well, realistically, we'll never hit that number with FPGAs. And nobody ever wanted to tell me a good thermal design point. But you have to design for something.
What I'd say, Mitch, is the way I'm looking at this on the thermal side of things is we've always said we're targeting a kilowatt for the processor on this module, right? And so all of our analysis is saying, can we get to a kilowatt, or and
Yeah.
we still
So
got
that-
a long way to go.
So the FPGAs are well below that, but then they need a lot of pins between them.
Yes, right. Well,
So-
that's where we've got the 320 transceivers. So we do the transceiver. So when I spoke to,
But that's usually not for emulation. That's not usually enough. 320
no.
lanes between
no,
FPGAs.
well. So don't forget these are 320 50 gig lanes. So there's two ways. So if you speak to when I was chatting to Paul about this, basically the big boys, they have two approaches. Either they use a shit ton of select IO between their devices, right? So they need many pins, and like 1,000 channels or more, or one of the others uses only transceivers between them for their emulation. So ours would be a transceiver only interconnect for the emulation between.
So did Paul kind of give you the nod where they're headed? Or like typical FPGA, they'll try to cover both of them.
They've got their big bad boy is a VP1902, is their big ASIC emulation FPGA, and that's the biggest device they make, and it's got 160 transceivers, and it's got 1,000 or so select IO. So they're catering for both their customers with this one device.
And do you know what they're running the SerDes rate at?
Yeah, they go up to 100. They go up to 112. But then you've got to divide the SerDes by 2. So take it as 50 gig per pin is what you get on average. 50 gig per transceiver in each direction, obviously.
Yeah.
So anyway, so we're really well set up for an ASIC emulation, right? And the other thing is, if you wanted to do an ASIC emulation where you said, I need a really shit ton of bandwidth between these two emulation FPGAs, well, with our cabling, you can actually do that. Whereas obviously, if you've got something like an OAM implementation, sorry, you've got a hypercube interconnect and that's it, mate. And you might not want that for your emulation. You might want a big fat lane between two of your emulation devices and a thin lane somewhere else. So I'm sort of getting more bullish on the application of an emulation platform that could. And then when we look at chiplet enablement, if you think about it, when people are now emulating their chiplet designs, they're taking maybe a monolithic design that they cut up into chiplets, or they look at a heterogeneous design. But you could emulate the entire system of chiplets in a big FPGA emulation platform. And then when you've got real chiplets to plug in, as long as you had a chiplet to FPGA bridge, you could make dedicated HPCM modules with the chiplets on, the real chiplets, and you replace the emulation pieces with real chiplet pieces, and you keep the emulation where you've still got chiplet under development. And so we used to, in the missile division that we did in British Aerospace when I was a kid, we did what we called hardware in the loop. And so that was where the guidance and control engineers would have a complete simulation of the missile system. And as real hardware came online, we plugged the real hardware into the big simulation model and see if it still worked. And so this is like, I'm translating that world to chiplet enabled world. So
maybe the FPGA, that emulation market might actually be a better one to target than the big GPUs.
Well, it's the natural. FPGAs are the most efficient accelerator of ASIC simulation. Call it emulation, and they're cycle accurate.
Well, yeah. I'm an old fan of that also, Alan. You know that from years past.
So now it's like I could do this myself, but it's like,
well, yeah.
And this is where I'm thinking of designing the card myself.
Yeah, I will. I mean, I get the emulation piece, and NVIDIA, our friends, threw a lot of weight behind that in a recent article. where they said they couldn't ship their silicon without doing lots of emulation because it'd take too long, because they don't validate their
So and
silicon.
I've got a number of
But it,
FPGAs, a number of accelerator startups, silicon startups that are
right.
all doing that path.
So they have to do the emulation, but if you go down the path of, oh, we're going to run AI on FPGAs, that analysis didn't turn out so well because of the inefficiency that they. Anyway, that's a whole different.
Yeah, but if you're just emulating
story.
your AI engine before you
right,
cut
right,
piece of silicon, then that's fine, right?
Yeah.
So actually, Matt, not to put you
You
on
just
the
got
spot.
you just got to find a startup that's got enough money to fund it.
Well, and it's not that much money, mate. I mean, this is what's driving me crazy.
Well, I know. It's the irony here, Alan, is that there's a handful of us running around that have been predicting this doom for over 10 years now, and we're running out of career, basically waiting for it to happen. And they just kick the can down the road just a little bit further, one more time.
Well,
but it just seems like it's gotta happen.
Well, in this this is a world. Well, I think this is where the FPGA does sing. Is it is the perfect accelerator for emulating ASICs.
Yeah. Well, there's definitely seems we're about out of town. There's definitely time, but there definitely seems to be a new round of funding that's going to roll into these AI startups, and it ought to be pretty substantial. In other words, you can't do it on.
Well, one thing I was just going to quickly ask Matt, if you don't mind, Matt, is you've had a little bit of a reputation of building or partnering with various board level companies to show you the stuff like your Firefly, etc., etc. Is actually building a little a test module, an FPGA HPCM module, if I could help you do it, be something that Samtech might want to do? And then, I mean, I guess it would mean that the idea would mean that you would have to want to get involved in leveraging the MCIO and making cables, a bit like you helped me and Mal out with FMC. Would you be prepared to help me out again with this?
That's a wonderful question that I can't answer in 30 seconds.
No, I realize that.
Frankly.
But I wanted to put a flea in your ear more than anything.
No, it's something that we would have to consider. I can't say yes, I can't say no. Alan.
So Alan,
it makes sense. I mean, the idea. Sorry, Mitch, I didn't mean to interrupt you. I apologize. I think the idea makes sense, whether it's us or whoever. But yeah, it makes sense. And I agree completely with you gentlemen. The thought process of using FPGAs for ASIC emulation, that's where the industry's going, right? I mean, if you look at what Synopsys and Siemens/Mentor and Cadence, all of their ASIC emulations are FPGA based, right? I mean, all you have to do is look at the annual reports for AMD and Intel and look who their big customers are, and that's a huge market for them. So I agree with Mitch and Howard that there's a great opportunity for this HCBM or however, sorry, I mispronounced that, for ASIC emulation.
It's a nice starting place, and then potentially, and it could be by itself, it could be a decent opportunity to make it happen, and then the rest of it could potentially come once we've got the infrastructure in place for the emulation engine. So,
Alan, not to use Cerberus again as a model, but this is a little bit less complicated than their
less complicated
than their chassis. Well, it's don't underestimate, so it took them 5 years to design their power cooling infrastructure.
Right.
And they can spin the chip in 18 months.
Right.
And so that's completely, you've heard this out.
Well, so by the way,
that's completely flipped from.
But to that point, these FPGAs don't burn that much power. So we could do a traditional on the chip side, we could do a more traditional copper lid with water running through it than doing this conformal coating.
Yeah. That's why I'm saying it's not
far more quickly with the FPGA, because I don't have to go all the way up to a kilowatt just yet. But we might have a so it's very doable in my head right now.
Well, you're working for an FPGA company now, aren't you?
No, well, no,
Is it
no,
an FPGA company?
they're a silicon startup. They're cutting their own ASICs,
Oh,
right? I mean, so
okay.
they're coarse grained reconfigurable, so they wouldn't do
Okay.
ASIC by any stretch of the imagination. Um,
Okay.
you know, because you want gate level emulation is what you want. Look, so
Yeah.
guys, actually, I mean, I haven't known you very long, Howard, but I've known Mitch and Matt for an awful long time, and they sort of know my history. I'm in a position where, or I'm in a thought process where I need to do another Nalatech, but I'm too old for that shit, man. And I want to help somebody else do it, or I want to help. That's why I'm doing this club of us all. And so I'm trying to work out a way to do this. I'm not sure if we could. I've not even bothered talking to VCs because I don't need the stress in my life. But I am passionate to make it happen. So and I don't necessarily need the money. I wouldn't mind getting paid a little bit, but I'm not looking for millions now. I'm too old for that. So anyway, if there's ways, I'm available. Like, so to you, Matt, I mean, if the management in Samtech say, well, this sounds like a good idea, and you want to pull the thread, you know, I'd be more than delighted to discuss any way to make it happen that you guys could enable. I mean, obviously, Mitch, you're well connected anyway with all of this. If you've got any,
I'm at a little, right, a little small startup that's 10 years into it. So
yeah,
we're pretty
no, I know
tight.
you are, but from your
yeah.
history, you're well connected, I guess.
Yeah.
And
Yeah.
Howard, I do know
Oh,
you've had, but if there's anything you can do to you know, from your, I'm not sure how much Lotus does beyond the interconnect, but again, you know, that's the idea of doing it here in OCP is like, can we club it together, and hopefully if we can be successful, then there's business for everyone out the back of this, in this new open standard.
Hey guys, I got to drop, so I appreciate the conversation. We'll look forward to furthering it in the future.
Yeah. Alrighty. Well, thanks.
Bye.
Yeah. We call
Yep.
it a wrap. Cheers.
Okay.
Good afternoon.
Thanks, Alan, Mitch.